next speaker, Professor Carla Gomez from Cornell University. It is specifically an honor for me because she's my PhD advisor and postdoc advisor and forever mentor. And so Carla has really been instrumental and a leader in establishing this new field of computational sustainability. And she's the PI on the 2 consecutive NSF expeditions in computing grants, which have supported growing this research agenda in this field with 2 10 million grants, which has been really great in order to be able to really get engaged and make the collaboration and the impact that we all want to do. And so she has a lot of insight into how this field has developed and what has made it work and what are the challenges, and she's going to share some of these insights with us today. Thanks, Carla.
Thank you so much for the introduction. So yes, I decided to talk, give a different perspective. But before I start, oh, by the way, let me start by saying, Melinda and Eric, awesome work. This is really very nice, your center and what you are doing. It's really fantastic. And, obviously it takes a village. And I really want to emphasize the importance of, collaborating students, partners, and the support of NSF. I have mentioned several times, when it comes to sustainability issues, it's not that easy sometimes to find funding, and NSF really has supported us even when working on sustainability was not that cool. They actually have supported us. And that allowed us to really, nucleate this field. And now we have a large network involving, several institutions. Cornell, Bowdoin, the lead is Mary Lou. Caltech, the lead is John Gregoire. CMU, the lead is Zico Coulter. Georgia Tech, Bistra. Howard University, Aziz, OSU, Tom was also part of our, was a lead in our first expedition. Princeton, Warren Powell, Stanford. It's nice to see so many here. Stefano there, UMass, Dan Sheldon. USC, Melind, and Vanderbilt, Doug Fisher. So, when basically, as given this is a doctoral consortium, I thought of, talking about how to, a different issue, how to advance computer science while doing computational sustainability research. I love computational sustainability and addressing sustainability questions. I'm a computer science. I really love doing computer science, and that's what I want to do. So I want to talk about how to, combine both. And when I was, I came up with the title, I don't even know when, but right away, and I really didn't think what I would talk about, but then I thought about a different talk that I gave. So this was a talk that I gave at the Grace Hopper conference, and it was, the title of the talk was, How Do I Become a Leader in the Field? Basically, this was a talk for undergrad students, postdocs, and junior faculty, and the setting was there were 3 women from different backgrounds, Deb at the National Lab, Irene at IBM, and in fact, she was the first woman to get a PhD from MIT, and my perspective was the academic perspective, and what I could talk about is how to do research. That's what I do for a living. And so, by the way, there's a nice little paper by Richard Hamming, Hamming distance, how you and your research that I truly recommend that you read. It's really an awesome paper. He was at Bell Labs, and very, very nice paper. There's also a little book that is supposed to be for women, but frankly, I think everybody should read it. Miss Menta's Impeccable Advice for Women in Academia. And I'll talk about some of the issues here. So we were supposed, to say what we do. So, I'm a professor at Cornell in computer science. And my background is really, my research, I have focused on large-scale automated reasoning, constraint reasoning, optimization, and integration also with machine learning, etc. So in my career, I really have focused on bringing together approaches from different domains. In fact, here is Exhibit 1, one of those posters for, you can see this was funded by the Air Force. And I did a lot of work. In fact, my tenure was really centered on that little Latin square problem. And I, studied that problem ad nauseum. But basically, I have been very much interested in combining techniques from different disciplines and actually learning about how the communities, for example, how OR has approached problems, combinatorial problems, and AI, and the trade-offs in terms of the different approaches. I like scaling up solutions, massive computations. I always tell that to my students. And I've done work on, exploiting structure, problem structure, and randomization. And, for example, here is I have this, Sebastian is, I was amazed how someone actually was working on stable distributions. Sebastian is working on stable distributions. I've done work on, heavy tails and how to exploit heavy tails to speed up complete search methods, which led to restarts, algorithms, etc. So you will see I'm a big believer in serendipity. Serendipity, I love that word. And you will see how the connection, how this nice little problem led me in part to sustainability, computational sustainability. So this was in 2008, we got the expedition. And so I talked a little bit about computational sustainability, how computational sustainability really, we are trying to develop computational methods to address such challenge in sustainable development, and the fact that often people think of sustainability or sustainable development as just environment, etc., but sustainability and sustainable development really encompasses environmental, economic, and societal needs. This has been stressed here because in the end, the ultimate goal is human well-being, and this is, you've seen this, the Sustainable Development Goals now this actually is from 2017, the updated version. So, fast forward to 2017, these are some of the projects that, I'm involved in, and you see we have projects in different areas concerning socioeconomic needs. In fact, we've been working on this project for a long time. Actually, Bistra, Stefano worked on this project, Yeisheng. I don't see Yeisheng here. There is Yeisheng. And, we have a project for understanding impacts of dams in Amazon. We have, collaborations, a lot of projects with the Lab of Ornithology, and also collaborations with Ecuador and Secretaria do Ambiente. That's actually, that's the environment, the Secretary of Environment. And we also have projects on advancing materials discovery for for renewable materials. So, this may seem like a quilt of projects, and that what's the rationale of this project. And this is one of my first points to you. I really think that in order for us to advance computer science methods, we really need to emphasize cross-cutting computational approaches and apply them to different problems. We focus on three thrusts, big data and machine learning. Obviously, now everybody really has to take advantage of big data. Constraint reasoning, automated reasoning and optimization, and citizen science, crowdsourcing, and multi-agent systems, because these are, often we are dealing with, systems involving, different perspectives, different agents, different players. And I've mentioned several times, we need to really find, cheap ways or inexpensive ways of collecting good data, and citizen science plays a key role. Well, so this again, and you can tell, how can you tell that this was submitted to NSF? Can somebody give me a hint that, or why this was in an NSF proposal?
It's a single word.
It is a single word.
No, not big data, that's two words.
It has transformative.
Yes!
Yes. Transformative, that's the word that you need to use. I do remember, maybe now I'm giving too much detail, but I remember when Bart read the first one, he kept saying, Carla, why do you use transformative all the time? And I said, you don't know, Bart. Yeah, indeed. This transformative word is key, but frankly, sometimes you use words and you start believing in them, and actually then you say, well, I said I would do this, so I better do it. And this is true. A lot of these projects, the traditional boundaries in terms of CS, where you have C, or you have machine learning, you have, automated reasoning, etc. Those barriers are, you need to really do research across those areas. And I think that is really what is exciting. How, how we bring together, techniques that, would be traditionally from different areas of computer science. So I really think that, the variety of projects allow us to have, these transformative synthesis across domains and applications, but also within computer science. And that, is very empowering. I think it's very powerful, and you feel empowered. And in fact, here is a different perspective of all the projects. Actually, these are the projects for the CompSysNet. You see here, for example, the green security games. You see here, for example, I think, Tom, are you going to talk about this today? The TAMO project?
Yes, briefly.
So, a variety of projects, and these projects now, the common thread here is the computational theme. And I'll talk a little bit about this more in detail. So now I thought I would give you some advice based on my experience, and I'm really going to start with very generalities, but I think they are important. But they are generalities. But and the first one is, work hard, no matter what. I mean, you really need to work hard if you want to succeed. And in fact, recently I read this article by the ex-wife of Elon Musk, And basically, she said, you know, this guy works hard, very hard. Yeah, so, you know, work hard. They say success is 90% perspiration and 10% inspiration. You know, persevere, go deeper into questions. You know, great work requires dedication, passion, and hard work. And, you know, it's good when you have a problem, and, you know, especially, you know, when you are a very junior, like a student, you think your life is busy. Well, you haven't seen what busy means. So you should really focus on a problem, obsess about it, and, you know, get rid of other things and tasks. But, you know, obviously also, you know, do sports, or that's good also, and or play music, you know, be balanced too. So, but, you know, really be passionate. You need to love what you do and believe in what you do, and really set goals high and say, you know, I can achieve great work. Of course, you know, sometimes you need to be courageous. There's some need to be courageous to really to ask the hard questions and pursue the hard questions. But, you know, above all, I think if you are passionate and you believe in yourself, which is my next point, you know, you need to be confident. By the way, and these slides, as I said, I used them for that talk at the Grace Opera, and, you know, I have to say that, you know, this is where maybe women sometimes, I don't know, women, little girls are always all focused, etc., but sometimes they are changed, and, you know, but I think it is important to be confident, and you know, I have to say, I didn't put it in red, but sometimes, you know, you find yourself saying, oh, I don't really know how to do it, oh, I can't do it, and no, I think you have to have confidence, but also a notion of, you know, how you can challenge yourself, but you don't have to, you know, have all the answers when you embark into questions, so into hard problems. And, you know, do not give up. Often the journey is really the award. Another key aspect is collaborations and networking. We've talked, I think we have emphasized that when it comes to computational sustainability, that is really important, because a lot of these projects are really interdisciplinary projects. We need to really have access to experts. In fact, I really emphasize this, and with my own students, I make sure that they collaborate with it, you know, the group, they all work together, or they work to collaborate with each other, and emphasizing different perspectives. Students and postdocs, it's fantastic to do collaborations, but you do have to check with your advisor before, you know, going on completely different directions. It's always good. It is very important for you to recognize the work of your collaborators. Sometimes people say, oh, they just gave me the data. That is not really what you want to do. You want to include everybody so they feel part of your project. And also, it's important, especially for more senior students, to get involved in, you know, writing research grants and collaborations. Networking is obviously very important. We already talked about that. And, you know, go to conferences, be part of program committees, etc. And for junior faculty, you know, NSF panels, it's a pain, but, you know, you need to really network. And obviously this meeting is awesome for that. Selling your work. Yeah, in Europe, you know, I'm European, I would not use this word, but yeah, you need to sell your work. And we already talked a little bit about that. it's not really good enough to do great work. I mean, you may do amazing work, but you need to really sell your work. Sometimes, actually, Papa Dimitriou has this line that the only thing people read from a paper is the title, often. So even the title has to be awesome, and put the message across. So it is really important to write very clear, pleasant papers, papers that people enjoy reading and they get excited about that. And of course, publish. That is important for students and junior faculty. Giving great talks, that is really important too. Your web page should be, your business card, but you should make everything available, papers, a nice web page, and, make all your algorithms and code available. We need to do that. This is very important. And here, again, borrowing from my experience with other communities, the satisfiability community really grow exponentially because of this, because of SAT Live, that is a site where, data, you have tons of data sets available, all the software. In fact, there are competitions, and the software, all the code has to be open source, and so that really transformed that field. Yeah, papers. Should you, for more juniors, may say, should you just have a seminal paper or publish more frequently? Some people say, oh no, you don't want just to spread to have too many papers, and you just want to go for seminal papers. Well, that's true, but there's a saying, your dean may not be able to read, but for sure your dean can count. so technical talks. Okay, technical talks. You work very hard on those proofs, on those formulations, and they are awesome. But you need to make talks that are, not heavy-duty technical talks. So you should have a good motivation for your problems, for your techniques, a high-level picture. Then you go a little, into technical detail, but then you do want to, put across the big picture and key ideas for the future. So even technical talks should be, pleasant and not really, too much technical detail that people get lost. So after graduate school, I do think it's good. I mean, it depends, but it's always good to do a postdoc, and typically you go somewhere else. Or, unless I have some exceptions, if you have, but essentially it is this is a time for you to be productive, write papers, etc. So a research lab is actually a good idea. I talked with Kevin about that. It's a good idea because you can focus on research, you can forge new collaborations, and if you, later on when you go to university, you probably don't believe me, my students, when I say, well, teaching and advising takes a lot of your time, but it's true, So be aware of that, and as you get more senior, you really, it becomes a challenge for you to have time to, to spend more than half hour thinking about a problem. And women, this is actually true for, because they all want, all these committees diversified, and women are asked to do all kinds of to be on committees, and we say yes to everything, and it does get a little overwhelming. And so, potential mistake: don't spend too much time on committees, teaching and advising. It is a balancing act. later on, as I say, actually, I was more thinking about, well, and let me not go there. So, but, you know, it is the committees, that is probably the issue that I would warn. Spending time with your students, advising grad students, this includes, that's a pleasure, you know, because that's your connection to actually doing the work and etc. So that's awesome. Committees, yeah, maybe I would cut on that. So, research, well, part of doing research is, you know, being able to deal with uncertainty, not having any idea what's, you know, what's the end. And tolerating this uncertainty and ambiguity is part of they are key components when it comes to doing research. So, but you know, in the end, it is a balancing act between you need to be confident, but you know, not too confident. You also need to be critical. And do listen to your advisor, because often the advisor, you know, has been there. And even do stay in touch with your advisor after you graduate, because in the end, your advisor is good. I mean, he or she will continue to really, you know, nurture your career, and that is important. Sometimes students, you know, move on and say, and then later on they say, oh, that was a big mistake. I should have kept in touch. So let me now go more to advice concerning computational sustainability. Several people have asked me, how did you get into this? And so I'm going to actually tell you that, well, before that, you know, my main message about computational sustainability is that, you know, it is really actually an amazing source of research topics for advancing computer science. You know, and in fact, you know, like at NSF, correct, Tom, we had to defend why is it that it's clear that computer science is going to inject techniques into sustainability and, you know, help solve some of those problems, and indeed we hope that we'll provide insights and methodologies and solutions to address these problems. But, you know, honestly, what is amazing is that it also leads to foundational contributions to CS, because we get new challenging problems, but also we learn new formalisms and concepts from other disciplines that are quite exciting often, but are not very robust from a computer science perspective. So that's where we come in. I'm sure that you heard some of the stories with Milind and Eric, and where the computer science, you guys provided the computer science framework. But you do get very interesting questions and methodologies that you can actually bring to the field. And we see this all over. And obviously, you know, the reward is we also have societal impact. So, you know, this is a great opportunity for us to develop new methods and ideas. So, now, a key issue, you know, you do want to relate your work to the communities you are interacting with. In particular, you know, you do want to know what's hot in computer science, and you want to relate your work to computer science and to the domain you are studying. Generalize, you know, often we work on a problem, and I do recommend that when you are tackling a problem, you really try to solve that problem, not an approximation or a variation, or, of course, you can use as a tool approximation algorithms, but try to solve the real problem, because that is how you make progress. And I'm going to give you a good analogy. You probably heard of Bell Labs. You know, why is it Bell Labs was such an amazing place? They actually were trying to solve a real problem, you know, communication, telephones. So that's why there was so much progress. I think we can use sustainability exactly to come up with very exciting questions, but then we want to solve them. But having said that, we should not really get lost into details, and we should try to look at the problems and generalize. And when you do that, not often you end up, you come up with more elegant solutions. And also keep in mind that science is cumulative. That means that you want other people to follow up on your work. So, and your techniques will apply to more problems. Diversify, you know, show that your contribution applies to different problems, and now, you know, more long term, now and then you do want to shift a bit your main research focus. I did that, for example, you know, my main focus was, you know, just combinatorial, you know, structures, and it's good for you to, you know, broaden your horizons. I have to say, you know, the students now are to some extent luckier because, you know, I think now it's becoming more acceptable, and, you know, you have all these awesome problems, so you can vary within this field. So, how am I doing? 5 more minutes. Bistra, how is this? I don't know, but I had 45 minutes. Somebody, should I blame somebody? No, it's okay. Anyway, so yeah, I had a lot more to tell you. But I'm going to, you know, this is a little problem that I use often as an example of all these issues that I raised here. And basically, this is also, you know, one way how I got into computational sustainability. You know, basically, I was asked to design experiments for fertilizers. And basically, the explanation is that, you know, the way you want to design experiments is to use Latin squares. I showed that before. But the experiments for Latin squares, you know, and I have studied this ad nauseam, and, you know, you need these special structures that are called spatially balanced Latin squares. And, you know, we thought that we could solve this problem very trivially, but we could not. And so the way, you know, so let me just tell you, I was so fast here. So Cornell actually plays this, is a land-grant institution, so they actually provide recommendations on how to use fertilizers, and there's a major project led by Harold Van Ness, who is a professor in crop and soil science. And I, you know, work with Harold on this. So, and he, you know, I gave a talk about my work and Latin squares, and he was all excited, and he said, oh, that's awesome, because we need to use spatially balanced Latin squares for designing experiments. And, but as I said, you know, we couldn't really, we tried all kinds of approaches, and we couldn't do this. So we had to find ways of doing this. And another detail, I, you know, was working on this problem when I had a major accident. In fact, that's why, in case you wonder, I always wear a scarf, because I had a major problem with my neck. And so I spent a lot of time looking at this little problem, and so it was awesome to, you know, keep your brain really busy and not worry about health. And, you know, discovering structure here. And by discovering structure, we could see symmetries, we could see all kinds of structure, and by imposing, so then what we thought, well, let's impose these constraints, and by doing that we kept, you know, solving larger and larger problems, and we could actually find the designs up to order 35. That's what they wanted. So, and now the question was, but how are we going to present this problem? And, I was working with, actually, in case you think I don't know how to spell Bart's last name, this is actually Meinhof Selman, a different Selman. And, and basically, Meinhof, very organized, we were thinking and writing about, how to design experiments for fertilizers. But, then we thought, wait a minute, I mean, we really need to look at the big picture and think about what we were doing here. But literally, the obvious thing that it would be, in fact, Meinhof had a draft on, how to use design experiments for fertilizers. But and this is what you always want to do. You want to think about, what you've done and how you can generalize it. So how can you frame this in the context of computer science? Well, so here is actually, you can tell this graph is, I remember doing this in PowerPoint, there's this odd little thing. Basically, if thinking about how we solve this problem, we had a problem that we could not solve because the search space was huge. So we kept adding constraints or imposing properties like, oh, now I want spatially balanced latent squares that are also balanced, and et cetera, et cetera. So we kept imposing constraints to, narrow the search space, and we call this streamlined constraint reasoning. And actually, that was the title of the paper. It had nothing to do with fertilizers. And actually, Meinhof was saying, Carla, we are just making up. And I said, no, this is really important because you start thinking about these ideas. And, another rule, always come up with at least maybe 2 other examples. So, right like an all-nighter, we came up with, streamliners for diagonally ordered magic squares, and actually Meinhof called Dumbledore squares or something like that. So always have 2 examples or 3 examples. And, this was really awesome, and now we had the idea of streamlined reasoning, which, by the way, now is used by several in different domains. But, now we were thinking, and the next question was, can we actually do this in an independent way? Because the way we were posing constraints was very much dependent on the particular domain. So can we do this in an independent way? And that led us to XOR streamlining, that is based on, a very beautiful result by Valiant and Vazarini that use, XOR constraints to prove that unique SAT is NP-hard. I'm going now to not go very fast. I'm not going to explain how this works because Bisso would stop talking to me. But basically, by making this, really general, this led to a lot of work, by us. Actually, Stefan really pushed this for probabilistic inference. Yashan pushed this for also sampling, and in fact, actually, Ronan, we had the conjecture actually that for the building latent squares, spatially balanced latent squares could be done with a construction, and he actually, using streamlining, found a construction. Here is a very large spatially balanced latent square. I will stop here. I'm just going to go to the end. How can I go to the end here? I didn't talk about so many other things, but here I'm going to just say, if you want to learn more about this, I'm giving a sneak preview to Yashan's poster, and it will I think he may talk about embeddings, which was yet another, idea that Yeshan came up with this idea by solving another problem, this AVI caching problem. That's and so again he generalized to come up with a methodology that is independent of any particular problem and that problem. Well, I'm not going to talk about this problem. This is, just another example. We are working on this materials discovery problem. This is like a source separation. Again, I really insist that we should look at related problems, and there we are working on other problems that are related to this materials discovery that is similar to a topic modeling problem. And because we are dealing with the scientific discovery problem, we really need to think, for example, about constraints, etc. But to summarize, I just want to say, this is really an exciting domain, and I think there are many opportunities for us to do great research and while advancing the state of the art of computer science. Thank you.